Welcome to my video lecture on Dirac delta function. Dirac delta function delta x is defined as delta x equal to 0 for x not equal to 0 and infinity for x equal to 0 with integration over delta x with lower limit minus infinity and upper limit plus infinity equal to 1. Thus, the Dirac delta function is infinitely high and infinitesimally narrow spike at origin with area equal to 1. Its property is f function of x delta x minus a is equal to f function of a delta x minus a, and integral over fx delta x minus a with lower limit minus infinity and upper limit plus infinity is equal to f function of a. Let's consider an artificial potential v function of x equal to minus alpha delta x, where alpha is some constant. One-dimensional time-independent Schrodinger equation is minus h cross square upon 2m d2 psi upon dx square minus a delta x psi equal to e psi. For e less than 0, we have bound states, and for e greater than 0, we have scattering states. Let's first consider the bound state for which e is less than 0. In the region x less than 0, we have v equal to 0, and therefore the Schrodinger equation assumes the form d2 psi upon dx square equal to minus 2me upon h cross square psi equal to k square psi, where k is equal to under root minus 2me whole divided by h cross. The general solution of this Schrodinger equation in the region x less than 0 is psi equal to a exponential kx minus kx plus b exponential plus kx. At psi, as x tends to minus infinity, the first term blows up, that is a becomes equal to 0, therefore psi is equal to b exponential kx for x less than 0. In the region x greater than 0, the general solution of the Schrodinger equation is psi equal to f exponential minus kx plus g exponential plus kx. As x tends to plus infinity, the second term blows up, that is g becomes equal to 0, and therefore psi is equal to f exponential minus kx for x greater than 0. The boundary condition for the wave function psi are: first, psi is continuous; second, d psi upon dx is continuous except at points where potential is infinite. Potential is infinite, right? The first boundary condition gives f equal to b. Therefore, psi function of x is equal to b exponential kx for x less than equal to 0 and b exponential minus kx for x greater than equal to 0. Psi function of x versus x graph has been plotted as shown here. Now integrating the Schrodinger equation from minus infinity to plus infinity, minus epsilon to plus epsilon, and taking the limit epsilon tending to 0, we get, after little bit of mathematics, delta d psi upon dx equal to minus 2m alpha upon h cross square psi 0. Since for x greater than 0, d psi upon dx is equal to minus bk exponential minus kx, so d psi upon dx on the positive side is equal to minus b into k, and for x less than 0, d psi upon dx equal to plus b k exponential kx, so d psi upon dx minus is equal to plus bk. Hence delta d psi upon dx is equal to minus 2bk, and psi at x equal to 0 is equal to b. Therefore, minus 2bk is equal to minus 2m alpha upon h cross square into b, and this gives k equal to m alpha by h cross square. The allowed energy is E equal to minus h cross square k square by 2m equal to minus 2m minus m alpha square upon 2h cross square. To normalize psi, we have mod psi square dx integral limits minus infinity and plus infinity equal to 1, and this gives b equal to under root k equal to under root m alpha upon h cross square h cross. Therefore, psi x is equal to under root m alpha by h cross exponential minus m alpha mod x upon h cross square, and energy E equal to minus m alpha square by 2h cross square. Now for the scattering state for which energy E is greater than 0. We have for x less than 0 the general solution of Schrodinger equation as psi equal to a exponential ikx plus b exponential minus ikx, and for x greater than 0 psi equal to f exponential ikx plus g exponential minus ikx. Continuity of a function psi at x equal to 0 gives us f plus g equal to a plus b. The derivatives of psi d psi upon dx is equal to ik a exponential ikx minus b exponential minus ikx for x equal to 0. So d psi upon dx minus is equal to minus ik a minus b. For x equal to 0, x greater than 0, d psi upon dx is equal to ik f exponential ikx minus g exponential minus ikx, and so d psi upon dx on the positive side is equal to ik f minus g. Hence delta d psi upon dx is equal to ik f minus g minus a plus b. At x equal to 0 we have psi 0 equal to a plus b. We earlier had delta d psi upon dx equal to minus 2m alpha upon h cross square psi at x equal to 0. This gives ik bracket inside bracket f minus g minus a plus b equal to minus 2m alpha upon h cross square a plus b equal to 2 beta k inside bracket a plus b, where beta is equal to ma upon h cross square k. So finally we have f minus g equal to a inside bracket 1 plus 2i beta minus b inside bracket 2i beta. Since g is equal to 0, we find b equal to I beta a upon 1 minus I beta and f equal to a upon 1 minus I beta. This gives reflection coefficient r equal to mod b upon a square equal to beta square upon 1 plus beta square, and transmission coefficient t equal to mod f upon a square 1 upon equal to 1 upon 1 plus beta square. Now we get r plus t equal to 1 and r equal to 1 upon 2h cross square e upon m alpha square, and t equal to 1 upon 1 plus m alpha square upon 2h cross square e. We see in these expressions that higher the energy, lower is the value of reflection coefficient and higher is the value of transmission coefficient. That is, lower is r and higher is t. T stands for probability of transmission. In classical scattering, if total energy E is greater than V max, then T is equal to 1 and R is equal to 0. The particle certainly makes it over. Conversely, if E is less than V max, then T becomes 0 and R becomes equal to 1. It rides up the hill until it runs out of energy and then returns the same way it came. But the quantum scattering problem is much richer. The particle has some non-zero probability of passing through the potential even if E is less than Vmax. This phenomenon is known as quantum tunneling. I have used here two references, that of Griffith and Eli Schiff. Thank you.